Analytic provenance records the history of analytical actions, showing how data was obtained, transformed, and analyzed. It can be visually encoded to help users track their ongoing analysis, recall past interactions, and inform new analytic directions. However, provenance is often hardwired into analytics systems, affording limited user control and opportunities for self-reflection. We thus propose modeling provenance as an attribute that is available to users during analysis. We demonstrate this concept by modeling two provenance attributes that track the recency and frequency of user interactions with data. To evaluate provenance attributes, we developed a visual data analysis system prototype, ProvenanceLens. ProvenanceLens enables users to visualize their interaction recency and frequency by mapping corresponding provenance attributes to visual encoding channels such as fill color and size, or applying data transformations such as filtering and sorting. Let's take a look. In this demonstration, we have loaded ProvenanceLens with a dataset of movies. From the data attributes view on the left, users can inspect attribute definitions as well as visualize corresponding distribution plots. To create visualizations, users can drag attributes to one or more visual encodings in the encodings view. In the resultant visualization canvas, users can hover on individual points and inspect them in the data records view below. To reduce their search space, users can also apply one or more filters in the visualization canvas. Now imagine the user performs such analysis for a while. Then, at some point, users may want to check if they have overemphasized or underemphasized certain movies and/or its characteristics. For example, what if they did not interact with any drama movies from the 80s? To alleviate these concerns, users can utilize provenance attributes from the provenance attributes view on the bottom left. Frequency tracks the frequency and recency tracks the recency of users' focus on data attributes and records. Users can utilize these attributes in the same way as they utilize data attributes. For example, let me drag frequency to fill. We immediately notice some points in the visualization canvas become darker than the others, indicating differences in the user's focus. By definition, darker points indicate a higher frequency score and hence more user focus. Using this encoding, users can spot areas where they have overemphasized and note areas where they would want to focus on next. Like data points, there are small glyphs in the attribute view that similarly encode the frequency score but based on the user's focus on data attributes. Darker glyphs once again indicate more user focus on the corresponding data attribute. Note that users can map frequency to any visual encoding, not just fill. For example, size, where bigger points indicate more frequency. Stroke width, where thicker points indicate more frequency. Even X, where points further to the right on the x-axis indicate more frequency. And so on. Not just visual encodings, users can also filter based on provenance attributes. For example, let me apply two filters, one that only shows uninteracted points and another that shows uninteracted attributes. Now as I interact with these resultant attributes and records, notice how they disappear from the interface one by one because they no longer match the uninteracted filter criteria. In addition to filter, users can also sort by provenance attributes. Like frequency, users can also leverage the recency provenance attribute to visualize the recently interacted data points and attributes. For instance, in the current configuration, darker points and glyphs indicate more recent interactions. Note that users are not bound to use one provenance attribute at a time. ProvenanceLens enables users to utilize both frequency and recency on multiple encodings and data transformations simultaneously. As part of our evaluation, we conducted an exploratory user study with 16 users to understand how provenance attributes are utilized for decision-making and self-reflection tasks. We find that using provenance attributes, users accurately and confidently answer questions about their analysis, and that mismatches between a user's mental model and the provenance encodings can be surprising, thereby prompting useful self-reflection. For more details, please read our paper. Thank you.